The question of the smallest possible measurement is not merely a technical concern of science. It is one of the deepest questions humanity has ever asked about the nature of reality. When we ask how small something can be, we are not only asking about numbers, units, or instruments. We are asking whether the universe itself has a fundamental limit, a smallest grain beyond which the concept of smaller no longer makes sense. This question touches the foundations of physics, mathematics, philosophy, and even human perception. From the earliest moments of human curiosity, people have attempted to divide the world into understandable pieces. A stone can be broken into smaller stones, those into pebbles, pebbles into sand, sand into dust. But does this process ever end? Or is there a final indivisible unit that forms the bedrock of existence? Ancient thinkers wrestled with this without experiments or equations, relying purely on logic and observation. Some argued that nature must be built from indivisible units, while others believed that division could continue forever. For centuries, science leaned toward the idea of continuity. Classical physics, particularly the framework developed by Isaac Newton, assumed that space and time were smooth, continuous backgrounds upon which matter moved. In this view, one could always imagine a smaller distance or a shorter moment in time. There was no theoretical lower bound. Measurement limits existed only because of technological limitations, not because of nature itself. This picture began to change dramatically at the beginning of the 20th century. As scientists probed matter at increasingly smaller scales, they encountered phenomena that defied classical intuition. Atoms, once thought to be indivisible, were found to contain electrons, protons, and neutrons. Later, even these particles were discovered to have substructure or deeper explanations through quantum theory. Each discovery raised a new question: is there an end to this chain? Quantum mechanics fundamentally altered how we think about measurement. One of its core principles, the uncertainty principle, tells us that there are limits to how precisely certain pairs of physical quantities can be known at the same time. This is not due to poor instruments or human error, but is built into the structure of reality itself. The act of measurement is no longer passive. It disturbs the system being measured. As scientists pushed toward smaller and smaller scales, they encountered a profound realization. To measure extremely tiny distances requires enormous amounts of energy. According to Einstein's theory of relativity, energy and mass are equivalent. Concentrating too much energy into a tiny region of space risks creating a black hole, effectively hiding the region we are trying to measure behind an event horizon. Nature itself seems to prevent us from probing beyond a certain point. This brings us to what is currently believed to be the smallest meaningful measurement of length, known as the Planck length. It is unimaginably small, far smaller than an atom, smaller even than the particles that make up atomic nuclei. To put it into perspective, if an atom were enlarged to the size of the observable universe, the Planck length would still be smaller than a grain of sand. The Planck length is not just a number pulled from experiment. It emerges from combining three fundamental constants of nature: the speed of light, Planck's constant, and the gravitational constant. This combination suggests that at this scale, quantum mechanics and gravity become equally important, and our current theories break down. Space and time themselves may lose their classical meaning. At the Planck scale, the idea of distance as a smooth, continuous quantity may no longer apply. Some theories suggest that space is quantized, made up of discrete units much like pixels on a screen. Others propose that space-time is more like a vibrating network or foam, constantly fluctuating at incredibly small scales. In such a regime, asking for a smaller measurement may be as meaningless as asking what lies south of the South Pole. Time, too, has a smallest meaningful unit, known as the Planck time. This is the shortest interval of time that can be meaningfully discussed using our current understanding of physics. Below this scale, the concept of before and after may no longer exist in any recognizable way. Cause and effect, as we understand them, could lose their meaning. It is important to emphasize that the Planck length and Planck time are not measurements in the traditional sense. They are not distances or durations that we can directly measure with rulers or clocks. Rather, they represent boundaries beyond which our physical theories cease to function reliably. They are signals that we have reached the edge of known physics. Some scientists argue that the Planck scale represents a true limit of nature, the smallest possible measurement. Others believe it is simply the smallest scale we can currently describe, and that a deeper theory, perhaps a successful theory of quantum gravity, may reveal even more fundamental structures. The debate remains open, and this uncertainty is one of the most exciting aspects of modern physics. String theory, for example, suggests that the fundamental constituents of reality are not point-like particles, but tiny vibrating strings, whose size is close to the Planck length. In this view, there is a smallest meaningful length, because strings cannot probe distances smaller than their own size. Loop quantum gravity, on the other hand, proposes that space itself is composed of discrete loops, forming a granular structure where area and volume come in smallest possible units. Despite their differences, these theories share a common theme. The smallest possible measurement is not merely a technological limitation, but a fundamental feature of reality. Nature may be digital at its core, even if it appears smooth and continuous at larger scales. This idea challenges deeply held intuitions. Human experience evolved in a world where continuity seems natural. We are accustomed to thinking that we can always divide things further. Accepting a smallest possible measurement requires us to rethink our understanding of space, time, and existence itself. There are also profound philosophical implications. If space and time are quantized, then the universe may be more like a computation than a continuum. Some thinkers have suggested that reality operates on informational principles, with the smallest measurements representing fundamental bits of information. In this perspective, physics and information theory become deeply intertwined. The limits of measurement also remind us of the limits of human knowledge. Science has achieved extraordinary success in describing the universe, yet it continually reveals boundaries beyond which our current concepts fail. These boundaries are not failures of science, but invitations to deeper understanding. It is also worth noting that the smallest possible measurement does not mean the smallest thing. Measurement is an interaction between observer and system. At the deepest levels, the distinction between observer and observed becomes blurred. Reality does not simply exist out there, waiting to be measured. It participates in the act of measurement itself. As we look to the future, new experiments, new theories, and new mathematical tools may reshape our understanding of the smallest scales. We may discover that the Planck length is not the final answer, or we may confirm that it represents an absolute limit written into the fabric of existence. What remains certain is that the search for the smallest possible measurement is ultimately a search for the foundations of reality. It is a journey that connects the infinitely small with the infinitely large, linking quantum particles to galaxies and moments of time to the history of the universe. In asking how small we can go, we are also asking how deep our understanding can reach. And perhaps the most remarkable lesson of all is this: the universe is under no obligation to conform to human intuition. It reveals itself only through patience, humility, and relentless curiosity. The smallest possible measurement, whatever its final form, stands as a reminder that even at the limits of science, wonder does not disappear, it intensifies.